So we are here with Yaakov Nahmias.
Good enough.
Good enough. Who is not only professor of the Hebrew University in Jerusalem, but also the founder of a lot of very interesting companies, organochip related and not. So thank you for taking the time with us to be here. And my first question is related to, so you started out actually as a chemical engineer or a chemist.
I still am.
You still am, right? By heart.
You never leave the profession.
So, and what made you go more into bioengineering and then finally taking up the field of organochip?
So chemical engineers usually try to solve problems in fluid dynamics and thermodynamics. That's what we do, right? We also have in-depth understanding of polymer science. All these three fields are tightly related to human physiology and human biology. So during my undergrad, I already took another degree in biology, which was my minor at the Technion, at the Israel Institute of Technology. And I was working on the development of a solid insulin formulation that ended up in one of Novartis's baby formulas. And then when I moved to the United States, I chose to focus on 3D printing of cells. So similar problems, similar approaches are needed, right? You need to understand flow, you need to understand thermodynamics, you need to understand polymers in order to push cells and print cells and understand how you can use them to form organs. For me, it was a natural evolution of what I'm doing.
I see that. And then something completely different. So let's have a quick chat about the liver meats. Can you explain what the goal is and how you found the motivation for this company?
Sure. So I was on sabbatical in MIT at the Broad Institute, 2016. I got a phone call from an investor that wanted to ask what I thought about the cultivated meat space. And I told him that I thought it was probably a very stupid idea. And he asked why. And I said, well, look, it's very expensive to grow cells. You need a lot of culture medium, and the minimum cost of culture medium is about $5 a liter. And you need about 20 liters to make a kilogram of anything. So, just by the plain numbers and mass balance, you'll get to $100 to $200 per kilogram. Where are you going to sell it? Elon Musk? So the investor was kind of upset, but I had time to sit down and think about the process from a very different perspective than everybody else in the field. So people were thinking about it from stem cells and tissue engineering. And I came to it as a chemical engineer, right? Thinking about what do we need to do to make it $5 a kilogram, $10 a kilogram. And it turns out if you're growing insects, or even insect larvae, you can do it for, $5 a kilogram. And that's because they have a liver. They have a mechanism to actually remove waste products like ammonia and lactate that are continuously generated. I designed back in 2016 the first system to rejuvenate culture medium and, reverse engineer the process of how do we get to the maximal cell densities possible? How do we get to the lowest cost media possible? And then patented it. And I had a good fortune 2 years later to meet the CTO of Tyson Foods. So Tyson Foods is probably the biggest meat company in the world. We were sitting at a conference and laughing about the futility of cultivated meat. And then, I said, well, over lunch, I said, I have an idea. And I charted out the design that we had. And he said, you know something? This is the first design that I ever saw that makes any sort of sense. And Tyson became the first investor in Future Meat Technologies at the time. And the company quickly grew. We became the fastest growing company in the market. And about 3 years ago, we raised $350 million, becoming the first unicorn, billion-dollar company in this space. And I was very involved all the way to last year. And now the company is building this massive factory in North Carolina and moving its operations to the United States. But it was a great experience.
And do you think that is also that, or in your opinion, does that really have the potential to replace meat in the long term?
Yes, I do, because
we need to considering the challenges we face also as
so
humanity.
Some challenges are exaggerated, others are not. So when you think about cultivated meat, people automatically talk about global warming and carbon. But if you don't want to deal with carbon, there are ways to deal with it, especially with cows, right? You know, everybody can start eating chicken, right? Chickens are not ruminating animals. They don't produce methane. That's not going to be a problem. The problem is that, you know, we are running out of water. For every 1 degree of warming, we're losing about 20% of fresh water across the world, including, by the way, Europe. So yeah, you see the glaciers on the Alps become smaller and smaller, and that means the rivers coming from them are becoming smaller. So we have less ability to grow cattle and to grow even chickens. So water is a huge issue, and that leads to a gap between supply and demand to the point where we have to find new technologies to make food that people want to eat. Because people can survive on soy and tofu, they just don't want to.
Otherwise, we would have already done it.
Otherwise, we would already done it. So that's the main driving force. And I think the technology that Believer develops and a couple of, you know, maybe one more company is capable of reaching, we'll be able to do it for about $6 to $8 a kilogram in the very, very close future. We had one paper in Nature 2 years ago and another one coming out this year, actually showing the cost-efficient manufacturing of this. So yeah, it's going to be fun.
Yeah. Then let's switch to a very different company from that. So Dynamics are
tissue dynamics.
So that seems like a very promising device to enhance the number of readouts for spheroids, organoids, and tissue slices. So in a bigger scale. And do you plan to also coordinate with other institutes or other companies for other models to like a bigger readout, like for example, the organoplate from Mimetas or the B-flow system from Beyond Chip? Like, is there something you're interested in?
So again, you know, when I form a company, it's usually because I think the field is going in the wrong direction. Okay. I was part of the team that developed the first technology of human on a chip on the market. So EUROoCS actually licensed my technology. It was the first chip with liver cells, you know, back in 2009. Several years before Emulate. And one of the biggest problems with organoid on chip is that they're trying to very accurately mimic physiology, which means that you can get precise data, but the throughput is very limited and the cost is very high. There is a need for another niche in this market. There is a need for massively parallel, high throughput robotic systems that can give you data that is maybe not 100%, but let's say 95%, but massive amount of it. So we developed organoids, very complex ones for liver, heart, brain, kidney, and we put sensors inside them, physically inside the organoids. So these are bionic organoids, kind of like Darth Vader, right? And then we can read those sensors in real time and actually get a very deep sense of what happens to central carbon metabolism, so to the main engine of every tissue. And the nice thing is that from a chemical engineering perspective, every tissue in the body, it doesn't matter if it's a brain or heart or liver, has exactly the same engine, right? Tiny fluctuations would actually affect the fuel utilization of this tissue. And then you'll be able to match that, fingerprint that to a mechanism of action. And we did it. And we did it with drugs for kidney that we found a mechanism that nobody believed exists. And it's completely different from mice. We took it all the way to a clinical study in Science Translational Medicine about 3 years ago. We did the same for the heart last year in August on Nature. Now we're publishing together with Abbott on COVID-19. Again, a mechanism that nobody else saw because it doesn't exist in rodents. And we can only do it because we went massive. We went like 20,000 organoids, right?
Because you have statistical power as well.
Because we have statistical power, that's right.
So your sensors, what kind of sensors are you using? Like, is there something you always monitor no matter what tissue are you interested in? And then there's something organ specific or?
Yeah, so we're not using biological sensors because those have, those are not always reproducible. So we're using electro-optical sensors. We have sensors for oxygen and we have sensors for lactate, glutamine, glutamate, and glucose. So all of the inputs and outputs of central carbon metabolism. So, and those are always the same and always constant. We spent 6 years and about $5 million, not only developing the sensors, but really standardizing them to the point where, there are very little fluctuations. And now they're very, very robust. So we can see tiny, tiny shifts. And it's a thankless job because you don't publish a lot. But when you publish big papers, right?
So what is your view on the future of organ on chip technology, and what would you like to change right now? What do you think should be included or excluded from going on now?
Wow. So first of all, I don't think that anybody should answer that question. There are people that have been devoting their lives for the last couple of decades to develop organ on chip, and there's been some very fascinating works coming out. What I would like to see as somebody with one leg in the field and one leg out of the field is clear cases where animal models fail and human-on-chip models succeed, and actually understanding why this happens. So clear cases where, the current models that everybody is using are not going to be good enough. And I think that's one of the things that we've been trying to do, and we're not the only ones. There's been a lot of labs trying to work on that. But if I was a young researcher, focusing on that, I would really try to find those cases where I can find a new physiological mechanism that will get me into the next textbook, right? I would try to find a new chemical mechanism that nobody saw before. Think about it like, we've been developing telescopes. Now point them in the sky and find something new.
Yeah. Okay, so rather than only replacing, so using organ on chip technology to replace animal models, also demonstrate where they can be even more advanced or can provide other information that cannot be provided by animal models. Is that?
Yeah, this is really what we need to do. We can't keep on saying that we are as good as animals. Nobody wants to hear that. If we're as good as animals, people will continue using animals. A mouse costs $1.50. A chip costs $700. Nobody's going to use a chip. You need to focus on exactly where the mouse fails and show that. Because once we have a massive literature of all the failures of animal models and how our technology can replace them better and manage to actually hit it on the nose, then people will be willing to pay $700 to take that chip.
Thanks.
It's my pleasure.
Thank you
It's
very
fun.
much. Yeah.